Alright, so today I'm going to be telling you about reduction of a phthalimide using sodium borohydride. So just a little introduction. So basically the end product in this entire reaction is going to be something that's useful in detecting amino acid concentrations. And this is just one step in the multi-step reaction. But this is the basic highlight of the reaction up here. And basically the purpose, what I'm looking at here, is examining the directive effect of the hydroxymethyl group on the reduction of the, I believe it's the third position carbonyl group instead of the first position, seeing that, you know, that is reduced and the other is not. So actually, let me just draw up here a little something what I'm talking about. So, yeah. So, oh, no, it's not working either. Okay, so. So this is basically, you have a carbon right here, and what happens in basic, reduction of sodium borohydride is the hydrogen electrons move to this carbon, and then boron has an unfilled electron orbital to fill its octet. So what I'm thinking is that this hydroxymethyl group with this nucleophilic oxygen here sort of donates its electrons to the boron, and that's why it chooses this carbonyl group over this carbonyl group, stability reasons. So did a bunch of simulations, mainly using VASP. I created the molecules using GaussView and ran them through all the simulations in VASP. This is showing the geometry optimization. I have movies here. The first two, this one's the reactant, it doesn't really show much movement, and the second one doesn't really show much movement either. This is the first intermediate, and the reaction mechanism I worked out by myself, just kind of thinking by stability reasons of where it would go. But in this third one, actually, the intermediate 2, it actually shows some hydrogen bonding to the methylene group, which is not quite what I expected. And in the product here, oh no, I might not be able to get it. Oh, here we go. You can actually see when it's developing on that there's some hydrogen bonding between the oxygen hydroxyl group and the other hydroxyl group, which create stability for the overall molecule. But the part I was kind of puzzled in is, if you look on the bottom, I have the energies of each on the bottom, and the lower energies seem to be the 2 intermediate groups, which kinetically doesn't really make sense, and the highest energy would be the product, probably due to the hydrogen bonding creates more energy within the bonds. But that just kind of leads me to believe that this isn't the right mechanism, and that this would not proceed in this sort of manner. Here's just a density states plot, sort of backing up what I showed for the energies. In each one, you can kind of see a different shift, and the higher energies being the intermediate to, or the product and the reactant, whereas the intermediates are sort of lower energies, which is odd. And here's the molecular dynamics I ran. You can clearly see some hydrogen bonding going on there, and there's not much to see with the other ones, but just kind of basic movement. Really the interesting thing is to see the hydrogen bonding between that molecule, because the product creates stability, which you would think would make the reaction proceed in the forward direction. So in conclusion, as I said, the bond energies don't suggest that the intermediates being lower energy, it would really proceed in that manner, because kinetically it doesn't really make sense. But really no evidence showing that the hydroxymethyl group sort of directed any kind of Borohydride reduction to that side. But ultimately, more research must be done in kinetics, and maybe some more on through computational chemistry in order to confirm what I've seen here, get a better idea of what's going on actually. So Q&A, questions?